and science takes the long way around so you do not have to rush anywhere at all. Wherever you are right now, whether you're stretched out in bed, resting on a sofa, or letting the day fade in the background while a small light glows nearby, you are exactly where you need to be for this moment. There is nothing you need to solve, nothing you need to remember, and nothing you need to prepare for. Just listening is enough. Tonight, we're going to spend some gentle time with something so familiar that it often goes unnoticed. Something that fills every room, spills through every window, and quietly follows you wherever you go. Light. Not as a switch you flip or a screen you stare into, but as something far stranger and more interesting than it first appears. We use it constantly without stopping to ask what it really is. We trust it to show us the world, to wake us in the morning, to guide us home after dark. And yet, when you slow down and look closely, light turns out to be one of the most puzzling things science has ever tried to understand. Before we go any further, take a moment to notice the light around you right now. Maybe it is dim and warm, coming from a lamp or a hallway down the way. Maybe it's the cool glow of a screen, or the faint spill of streetlights through a window, or perhaps the room is mostly dark with just enough light for shapes to exist without demanding attention. Where are you listening from tonight, and what kind of light is sharing the space with you? It is a simple question, but a fitting one. Light has always been tied to place, to time, to the feeling of being somewhere specific. If you find this slow exploration calming, interesting, or simply a pleasant way to unwind after everything the day has asked of you, you're very welcome to like the video or subscribe. It helps this small pocket of calm reach others who might need it too. There is no rush to decide. You can always think about it later. For now, just let the words arrive and pass, like light itself does. It might seem odd to devote so much attention to something that feels so obvious. Light is just there. You turn it on, you turn it off. It fills the gap between objects and your eyes, and that seems to be the end of the story. But that sense of obviousness is deceptive. For centuries, people argued about what light actually was. Some thought it must be a kind of substance flowing through space. Others believed it was a vibration of some invisible medium. Still others suspected it behaved more like a stream of tiny particles. Each idea worked well enough in some situations and failed completely in others, leaving behind a trail of confusion, debate, and surprisingly passionate disagreement. Long before equations and laboratories entered the picture, humans had a complicated relationship with light. Fire was one of the earliest forms of it that we learned to control, and with fire came warmth, safety, and the ability to push back the dark. The sun governed when people worked, rested, travelled, and gathered. Shadows became tools for telling time. The changing quality of daylight marked seasons, moods, and rituals. Light was practical, but it was also symbolic. It meant clarity, knowledge, life. Darkness, by contrast, meant uncertainty and rest, sometimes fear, sometimes peace. Even now, those old associations linger. We speak about seeing the light when something finally makes sense. We describe ideas as bright or dim. We talk about enlightenment, about being kept in the dark, about shining a light on a problem. All of that language grew out of the simple fact that without light, vision stops, and without vision, the world feels incomplete. Yet none of that tells us what light is made of. It only tells us what light does for us. Science, especially the slower, more careful kind, is often about separating those two questions. What does something do, and what is it really? Those answers do not always line up neatly. If you had asked a scientist a few hundred years ago what light was made of, you might have received an answer that sounded confident and reasonable at the time. Light, they might say, is a wave travelling through a medium, much like sound travels through air or ripples move across water. This idea had an appealing simplicity. Waves were familiar. They explained reflection, refraction, and the bending of light through glass. The only problem was the medium. If light was a wave, it needed something to wave through. Scientists invented an invisible substance called the ether to solve this problem, a hypothetical material that filled all of space, even the emptiness between stars. For a while this worked well enough. Then experiments became more precise, and the ether stubbornly refused to reveal itself. No matter how carefully scientists looked, they could not detect Earth moving through this invisible substance. Eventually the ether faded away, leaving behind an uncomfortable gap. Light behaved like a wave, but not like any wave anyone had ever encountered. Other experiments pointed in a completely different direction. Under certain conditions, light acted less like a smooth, spreading wave, and more like a series of discrete events, tiny packets delivering energy in specific amounts. This behavior made no sense if light was only a wave. It made much more sense if light consisted of particles. But particles came with their own problems. They did not easily explain interference patterns or the way light could cancel itself out in some places and reinforce itself in others. For a long time, science was stuck with an unsatisfying answer. Light seemed to be a wave when it was convenient and a particle when that worked better, refusing to commit to a single identity. This was not a matter of incomplete understanding that would soon be resolved with a clever experiment. It was a deep, structural problem that forced scientists to rethink some of their most basic assumptions about reality. As we move gently through this topic together, there is no need to hold all of that complexity in your mind at once. You do not need to remember names, dates, or equations. Think of this instead as a guided wandering, the kind where you follow a path not because you know where it leads, but because the walk itself is pleasant. Each idea will appear, settle for a moment, and then make room for the next one. One of the most surprising things about light is how fast it moves. Even without numbers, the scale is difficult to grasp. Light from the sun takes a little over 8 minutes to reach Earth. Light from distant stars can travel for years, centuries, or millions of years before finally arriving at your eyes. When you look at the night sky, you're not seeing things as they are now, but as they were long ago. Light is a messenger from the past, carrying information across enormous distances without slowing down or wearing out. That speed led many people to assume that light must be weightless, insubstantial, almost nothing at all. How could something so fast, so intangible be made of anything? And yet, light can push. This is not a metaphor. Light carries momentum. Under the right conditions, it can exert pressure, nudging objects ever so slightly. Solar sails, thin reflective sheets designed for space travel, use this pressure to move without fuel. Even in everyday life, the warmth you feel from sunlight is energy delivered to your skin by light itself. So here we already encounter a quiet contradiction. Light feels empty, but it carries energy. It feels immaterial, but it can push. It seems constant, but its behavior changes depending on how you observe it. These contradictions are not flaws in our understanding. They are clues. As you listen, you might notice your own attention drifting in and out. That is perfectly fine. Light does that too. It spreads, scatters, reflects, and sometimes slips past without leaving a strong impression. You do not need to follow every sentence closely. The general shape of the story is enough. At its most basic level, light is a form of energy that moves through space. That statement is accurate but incomplete. It is like saying that music is organized sound. True, but it does not capture the experience of listening, the structure of harmony, or the emotion carried by a melody. To understand what light is made of, we need to look at how it behaves, how it interacts with matter, and how it fits into the larger picture of the universe. Light does not require air. It does not require water. It does not even require the presence of atoms. It travels just as comfortably through the near vacuum of space as it does through your living room. This alone sets it apart from most other familiar phenomena. Sound needs something to vibrate. Heat usually moves through contact. Light is different. It is self-propagating, meaning it carries with it everything it needs to keep going. And yet, light is deeply connected to matter. It is produced when atoms change their internal energy. It is absorbed when electrons shift between allowed states. It reveals the structure of molecules, the composition of stars, and the movement of galaxies. Through light, we have learned what the universe is made of without ever touching most of it. That relationship between light and matter is one of quiet exchange. An atom emits light. Another atom absorbs it. Information moves without anything physically traveling between them in the way we usually imagine. No tiny beads fly through space like dust. No substance is transferred. And still, something real happens. This is where the idea of light being made of particles called photons begins to make sense. even if it feels counterintuitive. Photons are not particles in the everyday sense. They have no rest mass. They cannot be pinned down or slowed to a stop. They always move at the same speed. They do not age. They do not experience time. From the perspective of a photon, if such a perspective could exist, the moment of emission and the moment of absorption would be the same instant. That idea alone is worth pausing on. Light crosses the universe, but for light itself there is no journey, there is no duration. Emission and arrival collapse into a single event. This does not mean that time stops for the universe. It means that light occupies a strange position in the structure of reality, one that resists everyday intuition. As the night continues, we will return to this strangeness again and again, each time from a slightly different angle. For now, it is enough to notice that light is not built from solid pieces stacked together like bricks. It is not made of substance in the way wood or metal is. It is made of relationships, of interactions, of energy moving in quantized steps. You might find that as you listen, your thoughts begin to soften around the edges. Questions lose their urgency. Answers become less about certainty and more about coherence. That is a good state to be in for this topic. Light itself does not offer simple answers. It offers consistent behavior, reliable outcomes, and just enough mystery to keep the mind gently engaged. Let the glow around you remain just as it is. The story of light is already present in the room, bouncing quietly off walls, passing through glass, resting briefly on your eyes before moving on. There is no need to chase it. At first glance, the question seems simple, almost too simple to deserve this much attention. What is light made of? It sounds like the kind of thing that should fit into a sentence or two, maybe a diagram in a textbook, a quick answer followed by a reassuring nod. But the longer people have sat with that question, the quieter and more persistent it has become. Not loud, not dramatic, just present. Like a thought that waits patiently in the background, resurfacing whenever you think you're finished with it. Light is everywhere, and that familiarity makes it easy to assume we already understand it. You flip a switch, the room brightens, the sun rises, shadows shorten, a screen lights up, and information pours out. All of this feels practical, reliable, and well-behaved. Light shows up on time. It does what it's supposed to do. It rarely surprises us in daily life. Yet behind that dependable surface is a question that refuses to settle. When light travels from one place to another, what exactly is moving? That question matters more than it first appears to. It is not just about light. It is about how we decide what counts as a thing in the first place. Most objects you encounter are easy to categorize. A chair is made of wood or metal. Water is made of molecules. Air is made of gases. Even things you cannot see, like sound, can be described as vibrations in something else. There is always a material basis, something underneath that carries the effect. Light does not fit comfortably into that pattern. There is nothing obvious underneath it, no medium you can point to, no substance left behind after it passes. You cannot scoop up light or bottle it in the usual sense, and yet you cannot dismiss it as nothing either. It carries energy, it carries information, it can heat surfaces, trigger chemical reactions, and move objects ever so slightly. Whatever light is, it is doing real work. The quiet question hiding inside light is not just what is it made of, but what does it mean to be made of something at all? That question tends to surface slowly, especially when the pace of thinking slows down. It is the kind of question that does not demand an immediate answer. It invites you to sit with it, to notice where your assumptions begin to blur. Consider how often we equate being real with being solid. We trust things we can touch. We believe in weight, texture, resistance. Light offers none of that. You can see it, but you cannot grasp it. You can feel its warmth, but not its edges. It fills a room without occupying space in the way furniture does. Two beams of light can cross paths without colliding, passing through each other as if neither were there. That behavior alone already sets light apart from most things you're used to thinking about. Two solid objects cannot occupy the same space at the same time. Light seems to do exactly that without complaint. It overlaps, interferes, combines, and separates again, all without leaving marks or dents. This makes it tempting to treat light as something less than fully real, like a visual effect rather than a physical presence. And yet, remove light entirely, and the world you experience collapses into something very different. Vision disappears, colours vanish, distance becomes guesswork, the structure of your surroundings becomes vague and uncertain. Light is not an optional extra. It is woven into how reality shows itself to you. So the question persists: what is actually there when light moves through space? Is something travelling, or is it more accurate to say that something is happening? One way to approach this is to think about how light behaves when it interacts with matter. When light strikes a surface, several things can happen. Some of it may be reflected, bouncing away at an angle that depends on the surface. Some may be absorbed, transferring energy into the material and warming it slightly. Some may pass through, perhaps slowed or bent along the way. These interactions are predictable, measurable, and repeatable. They follow rules. Rules imply structure. Structure suggests underlying reality. Light may be elusive, but it is not arbitrary. It behaves in consistent ways, and those behaviors can be described with remarkable precision. That consistency is one of the reasons scientists took the question of light so seriously. If light were merely an illusion, a trick of perception, it would not obey such strict mathematical patterns. As experiments became more refined, it became clear that light carries energy in specific amounts. This was not always obvious. Early theories treated light as something continuous, like a wave on water, smoothly varying in intensity. But certain experiments refused to cooperate with that picture. When light interacts with electrons in atoms, the energy exchange happens in discrete steps. Not any amount of energy is allowed, only certain values work. This was deeply unsettling at the time. It suggested that light does not deliver energy as a smooth stream, but as individual packets. These packets came to be called photons, not because the name solved anything, but because it gave scientists something to talk about. Naming a mystery does not remove it, but it does make it easier to examine. Calling light a stream of photons, however, introduces its own set of problems. Photons behave nothing like everyday particles. They have no mass at rest. They cannot be slowed down. They do not follow simple trajectories you can draw on a piece of paper. They do not even exist in the usual sense between interactions. They are created, absorbed, and in between, they occupy a strange conceptual space. If that sounds vague, it is because the reality is genuinely difficult to describe using everyday language. Our intuition evolved to deal with objects that move slowly, bump into each other, and stay put when not disturbed. Light does none of that. It is not surprising that it resists easy description. Another way to approach the question is to ask whether light needs to be made of something at all. Perhaps that expectation itself is misplaced. Perhaps light is not a thing in the same category as tables and stones. Perhaps it is a process, a pattern of change, a relationship between electric and magnetic fields that sustains itself as it moves. This idea brings us closer to how modern physics often describes light. Light can be understood as an electromagnetic disturbance, a linked oscillation of electric and magnetic effect that propagates through space. No medium required, no substance flowing, just a pattern that maintains itself. But even this description raises questions. What exactly is oscillating? Electric and magnetic fields are not made of matter either. They are properties of space, conditions that describe how charged particles would behave if they were present. Saying that light is made of fields feels like replacing one mystery with another. At this point, it may be helpful to notice that the discomfort you might feel around these ideas is not a failure of understanding. It is a signal that you are brushing up against the limits of familiar categories. Light forces you to loosen the grip on the idea that everything must be made of tiny solid pieces. There is a quiet shift that happens when you allow for that. The world becomes less like a collection of objects and more like a network of interactions. Things are defined not only by what they are, but by how they relate to everything else. Light fits naturally into that picture. It is not an isolated object. It is a connector. When light leaves a source, it carries information about that source. Its color tells you something about temperature or composition. Its intensity tells you something about distance or power. Its direction tells you where it came from. In this sense, light is a messenger. It links events across space and time, And this brings us back to the quiet question. If light is a messenger, what is the message written on? What is the medium of information? One answer is that the message is written on the structure of the universe itself. Space is not empty in the way an empty box is empty. It has properties. It allows certain kinds of motion and forbids others. Light moves through space not because space is filled with something, but because space itself supports the behavior we call light. That idea can feel abstract, but it becomes more approachable if you think about other familiar patterns. A wave on a stadium crowd is not made of a substance that travels around the stands. People stand up and sit down in sequence, and the pattern moves. Nothing physical makes the full loop. The wave exists because of coordinated local actions. Light, in some interpretations, is similar. It is a coordinated pattern of change that moves through the structure of space. Nothing needs to travel the whole distance for the effect to propagate. Still, unlike a stadium wave, light carries energy. It can do work. That energy is not borrowed or symbolic. It is measurable and conserved. This is where the photon picture regains its usefulness. Photons give us a way to account for energy transfer without imagining a substance sloshing through space. So is light made of photons? Yes, and also no, depending on what you mean by made of. Photons are not building blocks in the usual sense. They are not smaller pieces that can be broken apart. They are indivisible events, interactions between light and matter that come in discrete units. You might think of photons less as objects and more as transactions. An atom emits a photon. Another atom absorbs it. The photon is the accounting entry that balances the energy books. In between, its existence is described mathematically, not materially. This perspective helps explain why light sometimes behaves like a wave and sometimes like a particle. Waves describe how probabilities spread out. Particles describe how interactions happen. Light is not switching identities. It is obeying a deeper set of rules that do not map cleanly onto either category. If this feels like an unsatisfying answer, that is understandable. Human curiosity often wants a clear picture, something you can imagine easily. Light does not offer that. It offers consistency instead. No matter how strange the description sounds, the predictions work. Experiments confirm them again and again. There is a quiet humility in accepting that some things are real, even if they do not fit neatly into mental images. Light invites that kind of acceptance. It does not demand that you fully grasp it in order to benefit from it. It simply continues to do what it does. As you listen, you might notice the way light in your environment has likely changed since we began. Perhaps your eyes have adjusted to the dimness. Perhaps the glow feels softer now. Light is interacting with you continuously, shaping your experience moment by moment without asking for attention. The question hiding inside light remains open, not because science has failed, but because the question itself keeps evolving. As our understanding deepens, the language changes. What once seemed like a demand for substance becomes a question about structure, interaction, and information. Long before light became something you could summon with a fingertip, long before glass bulbs hummed quietly in ceilings or screens glowed patiently in pockets, light arrived only when nature allowed it. It was not constant. It was not guaranteed. It appeared and disappeared on its own schedule, and people learned to shape their lives around its presence and its absence. In that older world, light was not a background condition. It was an event. Imagine a time when night was truly dark, not dim, not gently illuminated by distant cities or passing cars, dark in a way that erased edges and swallowed distance. When the sun went down, vision narrowed to what little light the moon and stars could offer, and even that depended on weather, season, and chance. Clouds could take the sky away entirely. A new moon could leave the land almost featureless. In those conditions, light was not taken for granted. It was watched, protected, and deeply valued. Fire was the first form of light humans learned to control, and that control changed everything. A flame was more than brightness. It was warmth, protection, and a signal that life was present. Fire pushed back predators. It extended waking hours. It created a shared center where people gathered, talked, worked, and rested. Light, through fire, became social. But fire was also demanding. It required fuel. It needed attention. It could grow dangerous if neglected. Its light flickered, shifted, and cast moving shadows that made familiar spaces feel alive and unpredictable. That flicker was not just visual noise, it shaped how early humans experienced the world after sunset. Shape seemed less fixed. Movement felt ambiguous. The boundary between what was there and what might be there blurred easily. In that environment, light was not neutral. It carried emotion. Warm firelight meant safety. Sudden darkness meant vulnerability. A distant glow might signal another group, a threat, or an opportunity. Light was information long before it was understood as energy. Above the fire was the sky, the second great source of light that shaped early understanding. The sun was not just bright, it was reliable. It rose and set with enough regularity that entire systems of timekeeping, agriculture, and ritual grew around it. The sun's movement divided the day into usable segments. Morning brought activity, evening brought rest. Light structured behavior. The moon offered a different kind of light, softer, colder, changing its shape over weeks rather than hours. It illuminated the night unevenly, sometimes generously, sometimes barely at all. Its cycles became markers of longer time. Months took shape. Tides responded. Animals adjusted their behavior. The moon taught people that light itself could change without disappearing. Stars added another layer. They were distant, fixed patterns that returned night after night, year after year. Unlike fire or the moon, they were unreachable. Their light arrived silently, steady and cold, from places no one could visit. Even without knowing what stars were, people understood that their light was old. It had been travelling long before it reached the ground beneath bare feet. In this pre-electric world, light was never uniform. It came in qualities. Firelight was warm and unstable. Sunlight was bright and directional. Moonlight was diffuse and uncertain. Starlight was faint but constant. Each type of light shaped perception differently. Colours shifted, depth changed. Movement was emphasized or lost depending on the source. Because of this, early humans did not experience a single version of the world. The same landscape looked different at noon, at dusk, by firelight and under stars. Light was not just revealing objects. It was actively shaping reality as it was perceived. This matters when thinking about what light is made of, because before theories and measurements, light was known through experience. People noticed how it behaved without naming why. They saw that firelight danced while sunlight did not. They saw that shadows stretched and shrank. They noticed that certain stones sparkled, that polished surfaces reflected, that water bent light in strange ways. These observations laid the groundwork for later questions, even if they were not framed scientifically. Why does light travel in straight lines until it doesn't? Why does it bounce off some surfaces and soak into others? Why does it break into colours after rain? These questions did not require microscopes or equations. They arose naturally from living in close contact with light's behaviour. Fire, in particular, taught an early lesson about light and matter. Flames produced light when fuel was consumed. Something was clearly happening at the material level. Wood burned, and light appeared. The connection between physical change and light emission was obvious, even if unexplained. Light seemed to be released from matter under the right conditions. This association lingered. For a long time, light was thought of as something that came out of objects, almost like a subtle substance that escaped when matter was excited, heated, or disturbed. That intuition was not entirely wrong. Modern physics still describes light as being emitted when atoms change energy states. The difference is that we now describe the process more precisely. The sky, meanwhile, offered a different puzzle. Sunlight arrived from above, constant and overwhelming. Unlike fire, it did not appear to consume fuel, at least not in any visible way. The sun rose every day without burning out. Its light did not flicker. It illuminated everything equally. This made it feel less like a process and more like a condition of existence. Many early cultures treated sunlight as fundamental, as something that sustained life directly. Crops grew toward it. Bodies warmed under it. Days revolved around it. Light was not separate from life. It was intertwined with survival. This intimate relationship meant that light was rarely questioned in abstract terms. It was accepted as a given feature of the world, like gravity or air. The idea that light itself might be made of something or governed by hidden rules was not obvious. Why question something so constant? Still, curiosity found its way in through small cracks. Rainbows were one such crack. They appeared suddenly, vivid and temporary, showing colours that did not normally exist in the sky. They did not belong to objects. They had no clear source. Light seemed to split itself apart, revealing complexity where uniform brightness had been assumed. Shadows were another source of quiet questioning. They were not objects, yet they had shape. They moved when the light moved. They distorted reality without touching it. A shadow could grow, shrink, stretch, or disappear depending on the position of a light source. This suggested that light had geometry, that it interacted with space in rule-based ways. Reflections added to the mystery. A smooth surface could create a second world, inverted and unreachable. The reflected light carried full detail, yet the image could not be touched. This hinted that light could preserve information about objects without being the object itself. All of these experiences built an intuitive understanding of light long before formal science. Light was consistent but not simple, reliable but not dull. It followed patterns that could be learned, even if they could not yet be explained. When artificial lighting eventually expanded beyond fire, first through oil lamps and candles, then gas, and finally electricity, something subtle changed. Light became stable, shadows softened, darkness retreated. The world stopped transforming so dramatically between day and night. Light became background rather than event. This shift made it easier to forget how strange light really is. When illumination is always available, its absence becomes the anomaly rather than its presence. The mystery fades into convenience, but the ancient experience still matters. It reminds us that light is not just a utility, it is a phenomenon that shaped human perception, behavior and curiosity long before anyone asked what it was made of. The question did not arise in a laboratory. It arose around fires, under skies, and in the slow noticing of patterns. As you rest with this idea, you might consider how different light sources still affect you emotionally. Warm light often feels calming. Harsh light can feel intrusive. Natural light shifts mood and energy in ways that are hard to ignore. These reactions are echoes of a much older relationship. Light does not just enter the eyes, it enters the nervous system. It regulates sleep, alertness, and internal timing. Long before it was measured in wavelengths or described with equations, light was shaping bodies from the inside. There was a time when the idea that light travelled at all was not obvious. It sounds strange now because movement feels like such a basic property. We see light leave a source and arrive somewhere else, so of course it must move. But for much of human history, light was thought to appear instantaneously. You opened your eyes, and the world was simply there. You lit a fire, and the glow filled the space without delay. There was no visible journey, no sense of motion in between. This assumption made intuitive sense. Everyday experience offered no hint of a pause between cause and effect. Strike a spark, and light appears. Look toward the horizon, and distant mountains are visible immediately. Nothing in ordinary life suggested that light took time to get anywhere. If it did move, it must have moved infinitely fast. That idea persisted for centuries, not because it was tested and confirmed, but because it was rarely questioned. When something works seamlessly, it tends to fade into the background. Light revealed the world so effectively that its own behavior escaped scrutiny. The first cracks in this assumption appeared not through deliberate experiments, but through careful observation of the sky. Astronomy has always had a way of stretching human intuition, forcing patience where immediacy feels natural. When people began to watch the heavens closely, patterns emerged that did not quite fit with the idea of instantaneous light. One of the earliest hints came from observing eclipses and planetary motion. If light were truly instantaneous, all visible changes should line up perfectly with their causes. But as measurements improved, small discrepancies appeared. They were subtle, easy to dismiss at first, but persistent enough to provoke curiosity. A more decisive moment arrived in the 17th century, when astronomers began tracking the motion of Jupiter's moons. These moons followed predictable orbits, disappearing behind the planet and re-emerging on the other side at regular intervals. Or at least they should have. What observers noticed was that these intervals were not perfectly regular. When Earth was closer to Jupiter, the moon seemed to appear slightly earlier than expected. When Earth was farther away, their appearances lagged behind predictions. The moons themselves had not changed their behaviour. Something else was introducing a delay. The explanation that eventually emerged was quietly revolutionary. Light, it turned out, was not arriving instantly. It was taking time to cross the additional distance when Earth was farther away. The delay was small, only minutes, but it was measurable. For the first time, light had been caught in the act of travelling. This realization carried profound implications. If light had a speed, then it was not just a condition of visibility. It was a physical phenomenon with measurable properties. It could be timed, it could be delayed, it could, in principle, be compared to other kinds of motion. Once the idea took hold, scientists began trying to measure that speed more directly. Early attempts were crude by modern standards, relying on rotating mirrors, distant observers, and clever timing tricks. But even with limited tools, the conclusion became unavoidable. Light moved extremely fast, but not infinitely so. This speed was astonishing. It dwarfed anything humans could achieve mechanically. Cannonballs, arrows, even sound itself moved sluggishly by comparison. Light raced ahead, crossing vast distances in fractions of a second. And yet, it still took time. That combination of near incomprehensible speed and finite travel was unsettling. It challenged the comfortable assumption that seeing was immediate. The moment light was understood to travel, the nature of space itself began to change. Space was no longer just a passive backdrop. It became something that light crossed, something that could introduce delay, separation, and structure. Distance mattered in a new way. At the same time, the idea of light travelling raised an immediate follow-up question. If light moves, what is moving? A wave must move through something. A particle must move through space. Which one was light? Early thinkers often favoured the wave idea. Waves were familiar. Sound was a wave in air. Ripples were waves on water. It seemed reasonable that light might be a wave as well, moving through some subtle, invisible medium that filled all of space. This hypothetical medium came to be called the ether. It was imagined as weightless, transparent, and everywhere. It had to be incredibly stiff to support the immense speed of a light, yet completely undetectable to touch or motion. It had to pass through matter effortlessly, while remaining fixed enough to define an absolute frame of reference. The ether was not introduced casually. It was an attempt to preserve intuitive ideas about motion and waves. If light was a wave, then something had to be waving. The ether filled that role. For a long time, this idea felt satisfying. It explained how light could travel through empty space. It allowed scientists to apply familiar wave mathematics. It fit neatly into existing frameworks. But there was a problem. No matter how carefully scientists looked, the ether refused to reveal itself. Earth's motion through space should have produced detectable effects, subtle shifts in the speed of a light depending on direction. Experiments were designed to catch these effects. They failed again and again. Light behaved as if there were no ether at all. Its speed remained the same in every direction, regardless of Earth's motion. This was not a small inconvenience. It was a direct contradiction. At this point, the story of light travelling took an unexpected turn. Instead of modifying the ether to fit the data, some scientists began to question the assumption that a medium was required at all. Perhaps light did not need something to travel through. Perhaps it was fundamentally different from sound or water waves. This shift marked a deeper change in thinking. It required letting go of the idea that all motion must be motion of something through something else. Light seemed to propagate itself, carrying its own structure along with it. The concept of electromagnetic waves offered a new way forward. Electricity and magnetism, once thought to be separate forces, had been unified into a single framework. Changes in electric fields produced magnetic effects, and changes in magnetic fields produced electric effects. These linked oscillations could sustain themselves and move through space. Light, in this view, was an electromagnetic wave. It did not need a medium because the fields themselves were the medium. Space was not empty in the traditional sense. It had properties that allowed these fields to exist and interact. This was a radical idea, but it worked. The mathematics predicted a specific speed for electromagnetic waves, and that speed matched the measured speed of light. The conclusion was unavoidable. Light was an electromagnetic phenomenon, and yet even this elegant solution did not settle everything. Waves spread out, they interfere, they can overlap. Light did all of these things, but light also behaved in ways waves should not. When light struck certain materials, it ejected electrons, but only if its frequency was high enough. Increasing intensity did not help if the frequency was too low. This behavior made no sense in a purely wave-based picture, where energy delivery should depend smoothly on amplitude. To explain this, the idea of light being quantized re-emerged, this time with experimental backing. Light energy came in discrete packets. These packets were later called photons. Here, the notion of a light travelling became more nuanced. Light did not travel as a stream of tiny bullets, nor as a continuous wave in the everyday sense. It travelled as a probability distribution, a structured pattern that governed where and how interactions could occur. Between emission and absorption, light followed wave-like rules. At the moment of interaction, it behaved like a particle. This was not a contradiction to be resolved later. It was a feature of how nature operates at small scales. Understanding this required a new way of thinking about motion itself. Light did not move through space the way objects do. It did not occupy positions in the same way. Asking where a photon was at a given moment was often the wrong question. Instead, light's travel was described by the evolution of fields and probabilities. The mathematics tracked how likely interactions were at different locations and times. The path was not a line, but a spread, a set of possibilities constrained by rules. Despite this abstraction, the consequences were concrete. Light took time to travel. That time could be measured, it could be affected by gravity, it could be stretched by motion. It was no longer just a messenger. It was woven into the structure of space and time themselves. One of the most profound implications of light's finite speed is that seeing is always seeing the past. The delay is usually tiny, far below awareness, but it is always there. When you look at an object across the room, the light reaching your eyes left it a fraction of a microsecond earlier. When you look at the sun, the delay is minutes. When you look at distant stars, it can be millions of years. This means that light does not simply reveal reality, it reveals history. Every act of seeing is an act of receiving information that has already travelled. This realization subtly changes the meaning of observation. You're not accessing the present state of distant objects. You're accessing a record carried by light across space and time. The universe, in this sense, is constantly communicating with itself through light. As tools improved, scientists learned to use this property deliberately. By analysing the light from stars and galaxies, they could determine composition, motion, temperature, and distance. Light became a probe, a way to learn about places no one could ever visit. None of this would be possible if light did not travel. Its motion is not an incidental feature. It is the reason light can function as information at all. Yet, the question of what exactly moves when light travels remains subtle. Energy moves, momentum moves, information moves. But a photon, as an object, does not travel through time in the way you do. It does not experience duration. This strange property sits quietly beneath all of modern physics. Light connects events without itself aging. It links moments without belonging fully to either one. As you listen to this, light is continuing to do this work effortlessly. Signals are passing from a source, reflecting off surfaces, entering your eyes, triggering cascades of activity in your nervous system. All of that depends on light's ability to move, and still, the movement is unlike any other. Light does not slow down, it does not speed up. It always moves at the same pace, regardless of the motion of the source or the observer. This invariance forced a rethinking of space and time themselves, but that story unfolds gradually, and there is no need to rush into it. For now, it is enough to notice that there was a moment, historically speaking, when light was first recognized as something that traveled. That recognition transformed light from a static presence into a dynamic participant in the universe. Once the idea that light traveled began to settle into place, another question followed almost immediately, and it was a question shaped by familiarity. If light moves, then how does it move? For most of human experience, motion that spreads outward follows a pattern we already understand. Drop a stone into a pond, and ripples expand in neat circles. Clap your hands and sound waves fan out through the air. Shake a rope and waves travel along its length. In every one of these cases, something moves because something else is being disturbed. Water moves up and down, air compresses and relaxes, the rope shifts its position. A wave, in everyday terms, is never just a wave. It is always a wave of something. So when scientists began to seriously consider that light might be a wave, they did so almost by reflex. Waves were familiar. Waves explained spreading, bending, interference, and patterns of brightness and darkness. Many of light's behaviors fit comfortably into this framework. Shine light through a narrow opening, and it spreads out. Pass two beams close together, and they interfere, creating alternating bright and dark regions. These were classic wave signatures. But very quickly, an uncomfortable detail made itself known. Light moved through empty space, not just thin air but near-perfect vacuum. Sound could not do this. Water waves could not do this. Rope waves could not do this. Every known wave needed a medium. Light did not seem to care whether one was present. To resolve this, scientists proposed something that, at the time, felt reasonable. Space itself must be filled with a medium, one so subtle that it did not interact with matter in obvious ways. This medium would support light waves just as air supports sound. It would be everywhere, filling even the emptiest regions between stars. It would be invisible, intangible, and undetectable by ordinary means. This was the ether, not the mystical substance of myth, but a carefully imagined physical entity designed to solve a specific problem. The ether had to be incredibly stiff to allow light to travel so fast, yet offer no resistance to planets moving through it. It had to exist everywhere but leave no trace. It had to be perfectly transparent and perfectly stationary. For a while the ether did its job. It allowed light to be treated as a wave without forcing scientists to abandon familiar intuitions. Equations worked. Predictions lined up with observations. The idea settled into textbooks and lectures. But something about it never sat quite right. The ether was never observed directly. Every attempt to detect Earth's motion through it failed. Experiments designed to measure slight differences in light speed depending on direction returned the same result every time. Light behaved as if there were no preferred frame of reference, no hidden medium setting the stage. At some point, the simplest explanation became the most radical one. Perhaps light did not need a medium at all. Perhaps the assumption that waves require something to wave through was the real problem. This was not an easy leap to make. It required loosening a deeply held association between waves and matter. It meant accepting that there could be waves that were not waves of anything tangible. Waves that existed as patterns rather than motions of substance. The breakthrough came with the understanding of electricity and magnetism. These forces, once treated as separate, were revealed to be deeply linked. A changing electric field produced a magnetic field. A changing magnetic field produced an electric field. Together, they formed a self-sustaining system. If an electric field changed in time, it generated a magnetic response, which in turn generated an electric response, and so on. This chain reaction did not require a medium in the traditional sense. The fields themselves carried the structure. The disturbance propagated because the laws governing these fields allowed it to. Light, in this framework, was an electromagnetic wave. It consisted of oscillating electric and magnetic fields, locked together, moving through space. Nothing physical needed to wiggle. The wave was not a motion of matter, it was a motion of influence. This idea answered many questions at once. It explained why light could travel through empty space. It explained why light always moved at the same speed. It unified optics with electricity and magnetism. It replaced the ether with a deeper understanding of space itself. And yet calling light a wave still carries baggage. When most people hear the word wave, they picture water or sound or a rope. These images are helpful but misleading. They smuggle in assumptions that do not apply. An electromagnetic wave does not consist of peaks and troughs in a substance. Nothing is piling up and falling back down. Instead, the wave describes how the strength of electric and magnetic fields varies from place to place and moment to moment. These fields are not material objects. They are properties assigned to points in space, descriptions of how charged particles would behave if they were present. When we say a field oscillates, we're not saying that something physically sways back and forth. We're saying that the influence changes in a regular way. This makes electromagnetic waves harder to visualize, but easier to accept conceptually once you let go of the need for a physical medium. The wave is the pattern. The pattern is real. One way to approach this is to think in terms of information rather than substance. A wave is a way information moves. In sound, the information is carried by air molecules bumping into each other. In light, the information is carried by the structured evolution of fields. That structure can exist even in emptiness. Space is not nothing. It has properties. It allows fields to exist. It allows interactions to propagate. Light takes advantage of that. When light spreads out from a source, it does so according to precise rules. Its intensity decreases with distance. Its wavefronts expand. Its phase evolves. All of this can be calculated, predicted, and confirmed. Interference, one of the most wave-like behaviors of light, offers a particularly clear window into this. When two light waves overlap, their fields combine. In some places, they reinforce each other, producing brightness. In others, they cancel, producing darkness. Nothing material disappears in the dark regions. The fields simply add up to zero. This behavior is difficult to reconcile with a particle-only picture. It makes perfect sense in a wave description, and yet, as comfortable as this explanation is, it is not the whole story. Light does not always behave like a smooth, spreading wave. When it interacts with matter at small scales, it behaves in discrete ways. Energy is exchanged in fixed amounts. Individual detection events appear as localized hits, not smeared patterns. This duality does not mean that light switches personalities. It means that the wave description and the particle description are both limited perspectives on a deeper reality. The wave describes how possibilities spread. The particle describes how outcomes occur. Between emission and detection, light behaves like a wave. At the moment of interaction, it behaves like a particle. Neither description is sufficient alone. Still, the wave picture remains essential for understanding how light moves. It explains why light bends when it passes through different materials. It explains diffraction, polarization, and the entire structure of optics. Without waves, lenses would not work, rainbows would not form, interference patterns would not exist. What makes light unusual is not that it behaves like a wave, but that it behaves like a wave without water, without air, without anything familiar to carry it. It is a wave of fields, and fields are not objects you can point to. They are rules written into the fabric of space. This realization quietly reshapes the notion of what it means for something to move. Movement does not always require a thing to change position. Sometimes it is the pattern that moves, not the pieces. Think of a stadium wave again. No single person travels around the arena. The pattern does. Light is similar but even more abstract. There are no people standing up and sitting down. There is only the pattern. This helps explain why light can pass through light. Two beams cross paths without scattering or colliding. Their fields simply add together and continue on. There is no traffic jam, no interference unless conditions allow it. It also helps explain why light can be polarized. The oscillations of its fields can be oriented in particular directions. This orientation affects how light interacts with materials, how it reflects, how it transmits. None of this requires a medium with fibers or grain. It arises from the geometry of fields themselves. As you listen, light continues to do all of this quietly. Waves of influence pass through the room, through walls, through air, through your body. They are mostly ignored, filtered out by your senses, except where they matter. Your eyes respond to a narrow slice of these waves, converting them into signals your brain can interpret. Outside that slice, light still exists, invisible but active, carrying energy, information, and structure. The idea of waves without water is one of those conceptual shifts that feels small at first and then keeps expanding. It suggests that the universe is not just made of stuff, but of patterns that can exist independently of substance. Light is one of the clearest examples of this, and yet, even this understanding does not fully answer the question of what light is made of. Fields describe behavior, not composition. They tell us how light moves, not what it ultimately is.